Hello, stats friends. Hopefully, things are going to plan. This is the beginning of our second semester, and I know it feels like we have a lot to get through, but we are precisely halfway there. So, sampling distributions is what Chapter 7 is all about. So we're going to start with exactly what is a sampling distribution, and we've looked at some things early on in the year where we did some random simulations for randomization and random simulation distributions. They're going to feel familiar, but they're not exactly the same thing. And this is where we're going to get really into vocabulary, and we got to be careful what we say. And by we, I mean me, because I'm as guilty as the next person of saying the wrong phrase. So first, let's get some vocab out of the way. We have something called a statistic and something called a parameter. So a statistic is a number that describes a characteristic of a sample. Isn't that cute that they put the S's together for us? That's nice. So it's for us to assume that a parameter is describing some characteristic of our population. So you're going to notice some notation, some symbols that are used, and we have to be careful that we're using the right notation. So anything that describes our sample would be called a sample statistic. And you're going to see things like X bar, which represents the sample mean, and P hat, which is the sample proportion, and S sub X, which is the sample standard deviation. In contrast to the population parameters, and remember the whole point of this is we're using sample statistics to estimate the population parameters. That's the idea. So mu is used for mean, and then a regular old p is population proportion, and then the lowercase Greek sigma is population standard deviation, which we saw back in, gosh, was that chapter 1? A long time ago. All right, so note, a sample statistic is sometimes called a point estimator of the corresponding population parameter because the estimate is a single point on a number line. So if you ever see that in a future textbook, perhaps you'll know what they're talking about. All right, let's look at this example here. So we're supposed to identify, now read carefully, we need to identify population and parameter and then the sample and the statistic. So the Gallup poll asks 515 randomly selected US adults if they believe in ghosts, and of the respondents, 160 said yes. So first let's focus on the population and the parameter that they're measuring. So the population that they're trying to hit would be all US adults. And then the parameter that they used, or that they're trying to estimate for the population is the proportion of all the US adults who believe in ghost. Now, they weren't actually able to ask all of the adults in the US, so they did a sample of 515 randomly selected uh, people there. So that's the sample, the 515 that were interviewed in the poll. And then the statistic was p hat, which we could calculate as the proportion who say they believe in ghosts. That's what they are measuring with their sample. So 160 out of 515 is roughly 0.31, I think. I don't know if it's exactly 0.31. I can't do that in my head. All right, so that's kind of the idea, and remember population parameter go together and sample statistic go together. So, oops, spoiler alert, there's the answers. So, part B, different question. During the winter months, the temperature outside of the Starness's cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during the given day. A minimum reading is 38. So for the population, I mean, what they're really trying to estimate is at all times of the day, um, what's the true minimum temperature at any time? So they need to figure out how low it goes. Now, the sample statistic is they sampled those 20 randomly selected times trying to measure where the minimum temperature occurred, which they found to be 38 degrees. So the hope is that that 38 degrees is a good estimator of what's really going on in the house throughout the day. So many students on the AP exam will lose credit when they're defining parameters because their description is actually referring to a sample instead of the population, or because their description isn't clear whether it's about which individuals the parameter is describing. So when you're defining a parameter, we suggest you include the words like either all or the true in your description to make sure that your reader understands that you understand you're not referring to a sample statistic. So we'll see some examples of that coming up when we look at some free response questions and some good answers and some bad answers. So like I said before, isn't math cute? S and P, they go together. So statistics come from samples and parameters come from populations. That's so cute. Good job, math. All right, sampling variability. So two words we've seen in isolation, but now we're going to put them together. So it refers to the fact that different random samples of the same size from that population will produce a different value for a statistic, which we've seen this before. So the example they're using here is they have a whole bunch of sample means, and I don't know what the premise of this problem was, but sample mean year n equals 5. So they took samples of 5, a whole bunch of them, and they created this distribution when they plotted all of the sample means that they calculated. So what we're seeing here is called a sampling distribution. So the sampling distribution of a statistic and the distribution of, of a statistic is a distribution of values taken by the statistic in all possible samples of the sample size from that same population. So I know sometimes we've done simulations where we know we didn't get every possible sample that was capable of being produced. That was a different idea, but I know what you're looking at here and you're thinking, oh man, that looks a lot like when we did that random simulation. It's a similar idea, but a different distribution. Hang tight. We'll discuss that in a moment. So there's a problem in your book that talks about John and Carol. They have 4 grown sons, and their heights measured in inches are 71, 75, 72, and 68. So first, they want you to list out um, all the possible sample sizes of size 2. So if I was to randomly select 2 of the sons, um, what sort of combinations would we have there? So here they are. You could have, and again, I don't have their names, but that's okay. I just want the data. So I could have the 71 and 75, the 71 and 72, the 71 and 68, or 75, 72, 75, 68, 72, 68. Notice they didn't reverse the order because that would be the same, combination. So we don't need to worry about that. So the next question says, calculate the mean of each of these samples and display them on a distribution like a dot plot. So the distribution of the sample mean is what we're looking at here. So the words that I'm using are important. This is a distribution of the sample mean of heights measured in inches. So calculating the mean, they just averaged the two, averaged the two, averaged the two, averaged the two, and then they plotted these means yonder and created a sampling distribution of the sample means. So now we're going to do something similar, and we're going to do the same idea, but now we're going to look at a different statistic. We're going to look at the range. So within those samples, now we're going to find the range. And range meaning just, we know it's not a negative distance, right? It's just the difference between them. So a range of 4, 1, 3, 3, 7, 4 plotted on a different dot plot. So here we have a sampling distribution of the sample ranges. Okay, now these are going to come into play in a problem coming up. It's going to be in our second day's lesson, but we're going to have to figure out whether in the future if our estimators are biased or not. So we'll come back to that idea later. This is a fun activity, and I believe there's an actual activity. Hopefully we have time to do it. I mean, it's January, I'm hoping, so I hope we have lots of time. So to determine how much homework time students will get in class, I love this activity, by the way. Ms. Lynn has the students select a simple random sample of 20 chips from a large bag. The number of red chips in the SRS determines the number of minutes that the students will get for work time in class. Ms. Lynn claims that there's 200 chips in the bag and they are perfectly proportional. There's 100 red and 100 not red, I guess. When Jenna selected a sample of 20 chips, without looking, she got 7 red chips. So of course, there's kids out there who are going to say, no, this is not, I know Ms. Lynn, they're wondering if she lied, basically. Does this provide convincing evidence that less than half the chips in the bag are red? Because if, Jenna selected 20 chips, we were anticipating 10 of them being red. But we know that's not how sampling works. But let's look at how we're going to answer this question. What is the evidence that less than half of the chips in the bag are red? So the evidence we have right now is Jenna's sample proportion, which we're calling p hat. The notation's very important. P hat is 7 out of 20, which is roughly 0.35, which does not meet our 0.5 that we are expecting. It's less than 0.5. So that's the evidence that they're using to initially claim maybe there's some convincing evidence that something's wrong. So provide 2 explanations for why that evidence is a thing. Well, it is possible that your teacher's not a liar. And Jenna just happened to get a sample proportion that was less than 50% because of sampling variability. Now that seems like the most logical and, the answer that makes me feel good. However, there is also a chance that Ms. Lynn is lying, and there are less than half of the chips in the bag that are red. So maybe Ms. Lynn has rigged this little sampling sampling activity. I doubt it. I don't think teachers really think like that. I think the sampling variability is probably the right answer. However, what would we be able to do to figure that out? Well, we'd have to investigate further. So for part C, they say there is one dot on this graph. And by the way, I should read the rest of the problem. We use technology this time to simulate choosing 500 simple random samples of size 20 from a population of 200 chips where 100 were red and 100 were blue. Again, this might ring some bells like, oh, we did that thing with the pieces of paper and that was different. That was a random assignment for an experiment. Same idea though, but this is, we're creating a sample proportion distribution. So we have a dot plot that shows all of the sample proportions um, for 500 samples. So on this particular, I guess it's a kind of a dot plot. It's a distribution. Let's just call it that for now. There's one dot that's at 0.8. What does that value represent? Well, that means in one of those 500 simulations, I'm sorry, my mother's calling. In one of those 500 simulations, where they pulled 20 chips, there were 16 red chips. So where'd they get the 16 from? Because they had to think backwards. Okay, 0.8 is 80%, and then like what out of 20 would have been 80%? So they did a little backwards math there. So part D, would it be surprising to get a sample proportion like Jenna got? So remember, Jenna got 7 out of 20 as 35%. Would it be surprising to get that or smaller? So when we look at our sample proportion distribution, 0.35 would be right here, right? Now, I don't have the actual count on this, but just kind of eyeballing it, there's quite a few simulated samples that had a proportion value less than or equal to 0.35. So no, I don't think we have evidence that that is an unusual proportion to get. So very similar to what we did with the statistical significance of our experiment data, but it's a different idea. I just want to stress that. So our final question, based on your previous answers, is there convincing evidence that less than half of the chips in the bag are red? So it's not surprising that we got that 0.35 because if we look at the simulation distribution, we're noticing there's quite a bit of chance in these simulations that it's going to happen. So it isn't surprising to get a p-hat less than or equal to 0.35 by chance alone when the probability is 0.5. There is not convincing evidence that less than half the chips are red. So Ms. Lynn is likely telling the truth. All right, so here's what I keep hinting at. Note, when we simulate a sampling distribution using assumed values for parameters, like we did, we assumed there was 50% of the chips. This is resulting in a distribution. The resulting distribution is sometimes called a randomization distribution. Okay. So now we got to get picky on what we call things. Let's be careful here. This guy here. This is I think I have a better slide coming up right here. Okay. So they're showing you the different types of distributions that we're going to be talking about. This first one, a population distribution, is measuring the parameters, but maybe we have distributions of sample data. So we have one sample where we pulled 20 chips, and I might have a different sample where I pulled 20 chips, and you notice the proportions are coming out different in every sample because there is a little variability. When we put all those together, we could create a sampling distribution that kind of gives us a better overall picture. So down here, the idea of sampling distribution is to take many samples from the same population, collect the data, the value of all the statistics from the samples, and display on a distribution. The dot plot shows an approximate sampling distribution of p-hat for that red chip problem. All right, here's what I was looking for, this guy. So population distributions gives the value of the variable for all individuals in the population. So this would be Um, Again, we're hypothesizing at some point in this, but that she had 100 red and 100 blue. But the sample, when they reached in and grabbed samples of 20, then we're looking at distributions of sample data, which allowed us to create statistics called p-hat. When we take all of the p-hats and put them together into another distribution, this is called a sampling distribution of the sample proportion. Yikes, that's a mouthful, huh? So distribution of sample data is one individual sample. When I put them all together, we have a sampling distribution. Yikes. All right, so exam tip. Terminology matters. Never just say the distribution. Always say the distribution of and then fill it in with the right word there. But be very careful to distinguish the distribution of the population versus sample data versus sampling distribution of a statistic. Likewise, don't use ambiguous terms like sample distribution, which could refer to a single sample data or the distribution of all of the statistics. So we have to be careful as to which one we're referring to, and you will lose credit if you're ambiguous, or even worse if you misuse a term. So we'll see some examples of free response coming up from this chapter, from this unit, where we can show you exactly what they're looking for. Wow, that is really blurry. I'm so sorry. All right, so we have a check your understanding. For those of you who are trying to watch the lesson from my class, this will probably be the end of day 1, is my guess, if you're looking for it, once we finish this question. But what we have here is, oh, candy company, my favorite. We got M&M's milk chocolate candies from Hackettstown, New Jersey. So they say the mix of M&Ms is 25% blue, 25 orange, 12.5% green, 12.5% yellow, so on and so on for red and brown. Wow, I didn't know that. And I think that's a true claim, actually. I feel a simulation coming on in our class, guys. I know it's COVID time, but I feel like we all could have a bag of M&Ms in our hands and we'd be just fine. All right, so assume that the company's claim is true and that you will randomly select 50 candies to estimate the proportion that are orange. So our first question is we're going to identify the population, the parameter, the sample, and the statistic, like we did early on in the lesson. Now this next one says graph the population distribution. I will tell you on your student notes, I went ahead and just gave you this because it's kind of a time-consuming thing to make the graph. It's not difficult to do, but like as a fellow non-artist, I don't really love making graphs on paper and pencil. And then part 3, we're going to imagine taking random samples of 50 M&Ms, make a graph showing a possible distribution. Now, what I already put on your student sheet is just one example of what could happen. You just have to remember that you're sampling 50 M&Ms, so like things have to kind of make sense. And the proportions, while we know what they say they should have, this is a sample of the 50 M&Ms, it's not necessarily going to match, right? And then part 4, oh, there's another part of the question. Give the value of the statistic for the sample. And then part 4, which of these 3 graphs could be the approximate sampling distribution of the statistic? Explain your choice. So I want you to pause the video, try at least numbers 1, and then, if you have your student notes, you already have 2 and 3 partially done, and then make sure you look at number 4 as well. All right, answers coming. All right, so the first answer, the population would be all M&M milk chocolate candies produced in the factory. And the parameter is the proportion of the M&M candies produced by the factory that are orange. Oh, apparently they wanted orange. I missed that part. Oh, yeah, right here, Abruzzo. That are orange. Duh. All right. So they were trying to figure out what proportion were orange. The parameter is claimed to be 0.25, and the sample is 50 M&Ms, and the statistic is a proportion of the sample of those 50 M&Ms that are orange. We're going to call it p-hat. So then for part 2, this is the proportion distribution as given by, you see the colors down here. Remember, orange was supposed to be 0.25. This is the proposed proportions. Now, part 3 is where they said create one possible graph showing possible distributions of sample data. So that would be like reaching in and grabbing 50 M&Ms. So this time they changed it to frequency over here on the y-axis. And if you took the time to add these up, they would have added up to 50 M&Ms if you're curious. Now for their particular example, they went with 11 orange M&Ms for no rhyme or reason. But then when they look at the proportion 11 over 50, that comes out to a p hat value, a sample proportion of 0.22. Now if you decided to go and make your own distribution for those 50 M&Ms, you very likely have a different number for orange, but the idea is it should make sense for the problem. So you might have a different answer for number 3, I guess is my point. And then I already forgot what 4 was. Which of these 3 graphs could approximate the sampling distribution of the statistic? Explain your choice. So they want the sampling distribution of the statistic. And spoiler alert, the middle graph is the approximate sampling distribution of p hat. The statistic measures the proportions of orange candies in the sample of 50 M&Ms. So assuming that that 25% thing is right, this is really hard to read. 25% here is in the middle. So we would assume, that Mars Candy Company is not lying to all of us, and that if we do a whole bunch of samples and we put them on our sampling distribution of the sample proportions, that we would see a distribution that kind of centers around 0.25. This one is really hard to read, but 0.25 is way over here. So this graph, unless Mars was lying to all of us, would not work, and this is not even the right type of graph. So there we go. A sampling distribution of the statistic would be a sampling distribution of the sample proportions is what they're looking for. That is a mouthful, right? Whew. All right, so that would be the end of day 1. Moving on to day 2, we're going to be looking at describing sampling distributions, and we're going to start with the idea of estimating using unbiased estimators. Okay, so a statistic used to estimate a parameter is an unbiased estimator if the mean of the sampling distribution is equal to the value of the parameter being estimated. So when they're referring to parameters, sometimes it's going to be the the proportion, the population proportion, the population mean, the population range, the population standard deviation. So we're trying to figure out if our samples data, the mean of it, comes out to the same thing as the population. Now, what we're leading into, if anyone has any history with stats, is we're getting towards inference, I guess, is the best way to say it. We're kind of opening the door to what's going to happen next, which is like a really big part of stats. I'll put it that way. So we're getting there, guys. We're almost there. So here's an example, that red blue chip problem. Again, if we took all possible samples of 20 chips from the population and calculated p hat for each sample, and then we found the mean of all those p hat values, we should get exactly 0.5. That was, again, remember that Miss Lynn problem where they were wondering if she was lying, and turns out she was not. So if we were to find the average of all of this, it would be 0.5. In the sampling heights problem with the John and Carol and their 4 sons, we created sampling distributions for the sample range of sample size 2. So if you remember, we took it's many slides backwards from here, but we took combinations of the 2 sons, we found the range of each of those samples, and then we created this little distribution. So if we took the ranges, these guys, and we averaged them, we found the mean, that's 3.67. Now, the question is the sample range an unbiased estimator of the population range? Well, the population would be all of their sons, and if I look at their data for their range, the tallest son was 75 inches and the shortest son was 68 inches. So the population's range is 7, and when I compare it to the distributions, okay, let me say this right. The mean of the sample range distribution, I don't think I said that right either. Anyways, the point is they're not the same. So it turns out that this is not an unbiased estimator of the population range. Okay, so that's a lot of words there to say what I just said really terribly. Because the mean of the sampling distribution of the sample range is not equal to the value it is trying to estimate, which is the range, population range, the sample range is not an unbiased estimator. Cool. To get a trustworthy estimate of an unknown population parameter, start by using a statistic that's an unbiased estimator. Okay. Unfortunately, Love that. That's a good segue. Using an unbiased estimator still doesn't guarantee that your value of your statistic will be close to the actual parameter. So we prefer statistics that are that vary less from the actual parameter. And we know from our previous work that larger random samples tend to produce estimates that are closer to the true population value. So instead of taking teeny tiny samples, take larger samples. So here they're showing the distribution of the, let's see what we got here, sample proportions. If they took sample sizes of 100 compared to sample sizes of 1,000, notice the variability is cut significantly. And that allows you to have a much better estimate for the parameter of the population. So in many cases, it's obvious which statistic should be used as an estimator. So we showed an example earlier about how, um, we could prove something was a biased estimator, but, so how do we get an unbiased estimator? What do we get a good one? So they're saying it's obvious. Let's take a look. If we want to estimate a population proportion P, then you should probably use the sample proportion P hat. Yeah, that seems pretty obvious. See, I love math. Oh, I need to delete that. That's random extra text for no reason. If we want to estimate the population mean, then it would make sense to use the sample mean of X bar. I just love math. All right, so this diagram, I think we've discussed this a little bit back in like collecting data chapter. And I know you've seen this in your science classes. It's the difference between being precise and being accurate. So to decide which estimator to use when there's several reasonable choices, consider bias and variability. So what they show here is bias means that our sample statistics do not center on the population parameter. So like over here, this is an example where there's not a lot of variability. All of, the marks are in the same spot, but they're supposed to be here. So there's some sort of bias that's pulling it off. So this is not an accurate estimation. So here, this, I guess in terms of math, you could say it's an accurate estimation, but it's not precise. There's too much variability. I feel like I need to get one more thing. There we go. Over here, this example is neither precise nor accurate. It's not even close to where it's supposed to be for the accuracy, and it's not precise because there's still a lot of variability. And then finally, you get the bullseye. So this is a measurement that is both precise and accurate. And here comes the warning, I bet. Oh, yes. Exam tip. There's a lot of kids who misuse the words accurate and precise. So their example here is a respondent might say, increasing the sample size will make an estimate more accurate. That's not the right way to say it. Increasing the sample size would make an estimate more precise. Now, their advice is if you can't remember whether it's one or the other, don't use those terms. Just explain in normal people language what you're trying to say, even if it's like really wordy and it sounds like you don't know what you're talking about. Sometimes that's better than using the wrong vocab term because you will definitely be dinged for the wrong vocab term. And if you can kind of run around the bush and explain it a little bit, then you very likely will get your point if you've made your point even a little bit clear. All right, checking our understanding. This is the last part of our lesson. So we got a good old histogram set here of the intervals. I feel like we've seen this problem before. Eruptions of Old Faithful from all 222 records of eruptions during a particular month. So that is a set of that's samples, right? It's not everything, but for this population, the median is 75 minutes. We use technology to take 500 simple random samples of size 10 from the population. Okay, I misspoke. They're calling it a population. My bad. So 500 simple random samples of size 10. And then the 500 values of the sample median are displayed in the histogram on the right. So the mean of those is 73.5. Okay. So first question, is the sample median an unbiased estimator of the population median? Ah, that's a fun one. And then we got to justify our answer. And then part two, suppose we had taken samples of size 20 instead of 10. Would the variability of the sampling distribution or the sample median be larger, smaller, or about the same? And then we got to justify, try using the right words on that one. And then part 3, describe the shape of the sampling distribution for the of the sample median. So they want the shape over here described just like we used to do back in chapter 1. All right, pause the video, write down some thoughts. I'm about to show the answers. So the first question about is the sample median an unbiased estimator of the population median? So remember they gave us here the mean of these 500 SRSs is 73.5. So if we compare that to the population median, which they did tell us up here is 75, I know they're close, but they're not equal. So therefore, we do have to say it is not equal to, so it's a biased estimator. Sometimes they write it as not unbiased estimator, but that means it's a biased estimator. So just watch your wording there. I know they're close, but not, they have to be the same. So part 2, suppose we had taken, so we increase our sample size. What would that do to the variability of the sampling distributions of the sample median? So if we increase the sample size, that will decrease the variability in the sampling distribution because larger samples provide more precise estimates. Hopefully you use the word precise and not accurate there. Because larger samples, and this is the reason why, larger samples include more information about the population. Okay, that's why they're more precise. Makes sense. And that's what, remember their warning, like if you weren't sure what word to use, if you could describe this to me in your words, that would get you the point. All right, and then the third question, describe the shape of this green guy over here. So it is skewed to the left, and they're saying it has a single peak. So they're not looking for anything dazzling there, guys, just old school description of the shape. I know, it feels like that's such an easy question at this point in the year, but you do want to bring back that old information that we used to use back in chapter 1. And that's it. Time flies when you're having fun. All right, so this is just the beginning of the chapter. We still have 2 more sections. It is a great lead in to what we're going to start talking about next. And I think you guys will really start to enjoy what we're going to do over the next few months. All right, good luck, everybody.